ourselves also, because everything is like a remote and online mode. So that physical integration or that vibes are missing. So I will try my best to be more lively and to have your effective participation in this lecture. And thank you very much for Government Engineering College of Valsad for organizing this faculty development program on electric system. This is a very timely course, and this course is going to contribute on how we have to increase penetration of electric vehicles, and for that purpose, what type of policies we need, what type of infrastructure we need, and at the same time, also we have to think from the manufacturer point of view also. So my objective in today's lecture is that, let's say we have the electric vehicles, and these electric vehicles are manufactured by some car makers and like that. And as a user, we have to consider like it is a black box, or we cannot change the configuration within the electric vehicles. But as a user of electric vehicles, we need to charge, or we need to provide the energy to the electric vehicles. And for getting that energy to the electric vehicles, as a user, right, what type of opportunities we have available? So first opportunity is going to be that how we have the electric vehicle charging system. In the electric vehicle charging system, the car manufacturers, right, they may not have that much role. Their role be maybe on designing the energy management strategies or energy management algorithms, or the hardware and software both, for the electric vehicle. But when we want to pump the power in the electric vehicles, then there is going to be a very big challenge. And I believe that the participants, they are from the most of them are from the electrical engineering background. So therefore, for them, it is going to be very easy to understand that how we have to do the electric vehicle charging in a coordinated way using renewable energy sources within the distributed network, so that we will not overload the distribution network. We may not need to enhance the capacity of the distributed network. So all those points I'm going to cover in this lecture. And if you have any questions or any doubt, so we will try our best to have further discussion on this one. Is it okay? And Harshad has given my introduction, and briefly I will tell you about my background also. At this moment, I am working as a full professor in smart grid and renewable energy at the Faculty of Engineering and Science, University of Agder, Norway. Before joining the University of Agder, Norway, I was working with University College London, School of Energy and Resources. And at the same time, I was also a member of South Australia government's first renewable energy board. And before that, I was lecturer at University of Dundee, Scotland, where my responsibility was to develop the master's and bachelor's program in renewable energy. And before joining the University of Dundee, I was with University of Jyväskylä, Finland, as a research director, and where I actively worked on developing hydrogen fuel-based charging station for fuel cell vehicles, and also to test the operation of fuel cell in the Nordic climatic zone. And before coming to Finland, I was in Canada, and there I was a research fellow, and I was working in Canada as a at Hydrogen Research Institute, University of Quebec, Toribia. And before moving to Canada, I was in India and I worked for some time at MA National Institute of Technology, Bhopal, and I did my education at IIT Delhi. So you can say that I am totally made in India and now working for the globe. And main focus of my research is more on sustainable development, or how we can use the sustainable technology for achieving the United Nations Sustainable Development Goals. So here now we are talking about electric vehicle system. So it is going to contribute on sustainable transportation, clean energy, reducing the greenhouse gas emission, and at the same time, then my lecture is also going to cover some aspects of integration of photovoltaic system. So that is my background. And another thing which I would like to share with you, two of my PhD students, they are working on developing the architecture and algorithms for coordinated electric vehicle charging system where we can utilize the photovoltaic system. And another student, she is working at Austria, and her objective or her PhD objective is that within the distributed network, how we can have the coordinated electric vehicle charging, considering the grid constraints as well as the energy pricing also. So here on the first slide, I tried to give you the overview, a high level overview of my background, as well as how my research work is going to contribute towards the sustainable transport. Okay? So now we will move forward. And there are a lot of challenges due to the electric vehicle penetration. So the positive impact, there are quite. For example, it is going to be the clean, and it is going to provide a solution to rapid increment of cost of fossil fuels. As we have seen that now the petrol prices are increasing, or the gasoline prices are increasing very heavily. So therefore, the electric vehicles can be a very good solution or application for that one. And of course, when we have the electric vehicles, if we consider from the emission point of view, so we are going to have less contaminants in emissions. And of course, we are going to have more high performance due to advancement of batteries. And electric vehicles is more going to be a very good contributor towards the sustainable transportation. And then the key challenge what we are going to face with the increasing penetration of electric vehicles is that uncoordinated charging, right? When we have too many electric vehicles and everyone want to charge at the same time, then we are going to face a lot of problems because it is going to increase a very heavy load within the distributed network. And we know that we have the limited network capacity. And of course, it is going to impact the power system stability and quality also. And we know that the electrical energy pricing, it is also the dynamics. So electricity market operation is also going to be changed due to the increasing penetration of electric vehicles. So those are the quite negative impacts. And before moving or before having sustainable or very high amount of electric vehicles penetration, right, we need to solve this problem in a very systematic way. Okay, not only just announcing the policies that we should have the more electric vehicles and like that, but before that we need to develop proper infrastructure for that, so that the users, they can have the reliability of the energy supply to the electric vehicles. One point. Second point, the distributed network or the electrical energy network should be in a position to cope up with the increasing demand of the electric vehicles. As we know that at this moment in many parts of the India, we have a lot of blackouts also. power loss also, and load shedding also, right? So those load shedding, power loss or generation demand gap, right? Those are going to impact the increasing penetration of electric vehicles, and the user may not be in a position to get electric vehicle charging at a time when they want to have charging. So therefore, we need to have appropriate coordinated charging system. Okay, then these electric vehicles are going to add extra load to the network, and therefore network reinforcement or reconstructions may be required. Okay? And due to this electric vehicle charging, especially within the distributed network, there is going to be line congestion within the distributed network. Similarly, electrical losses are going to be increased, and of course the thermal loading of the transformer is also going to be increased. So to move forward, right, to have more substantial amount of electric vehicles, we need to solve these problems. And for that purpose, from the academics point of view, we need to contribute in a very systematic way by developing the coordinated electric vehicle charging system, considering the grid constraints, taking into account that distributed network capacity is not going to be changed. Okay, how we can utilize the distributed energy resources, for example, solar photovoltaic, fuel cells, or any other source in a coordinated way so that we can reduce the demand of electric vehicles on the main grid. And also we need to consider that how different type of pricing mechanism has to be introduced within the distributed network, especially for the electric vehicle charging system. Then another point which maybe came to in your mind, that so how we have to design the electric vehicle charging station. So this electric vehicle charging station, some consumers or some customers or some owners, they may charge their electric vehicles at their home. So that may be the slow charging. Second option is that to have the fast charging at a particular station, where we can say, let's say we have the hybrid options where we can have the petrol charging also, petrol filling also, or the diesel filling, and as well as having the facility for the electric vehicle charging. Then another thing, like if we take the urban area or the institutional area, or maybe in the shopping centers and like that, then of course we know that many people, they are going there by the car, and then how we have to utilize that facility for us. So here I'm going to use some examples and how we have to develop the electric vehicle charging scenarios or the architecture by reducing the demand on the main network, and how we can utilize the local energy resources, and how we can do the coordination of charging between different electric vehicles. Is it okay? Everything is coming okay now?
Yes, sir.
So now here I'm on the third slide. So in the third slide, there are two options have been given. Like one option is centralized EV charging coordination, and second option has given as a decentralized EV charging coordination. So how the centralized EV charging coordination, and whether it is good to have the centralized EV charging, or whether we should go for the decentralized charging station. Of course, the decentralized EV charging station is going to provide more flexibility to the users, but centralized electric vehicle charging coordination is going to provide more flexibility to the grid or to the grid operator. So we will consider both, and we will see how both can be worked together, or how we can have the hybrid options also. So let's say, let's come to the first point of a centralized electric vehicle charging station. In the centralized electric vehicle charging station, basically the idea is that this electric vehicle load has been considered as a power intensive load. When we have the power intensive load, we can, and it is not that critical also, because it has the battery bank already and there will be some reserve at the same time. So due to that, it has the opportunity to operate or to make the operation of charging, right, by using centralized approach. So how the centralized approach it works, that I will try to explain you briefly. The centralized EV charging coordination, it works more like centralized demand side management scenario. With reference to this point, before I had one project which was funded by European Union Framework 7, and that project it was called Scalable Energy Management Infrastructure for Aggregation of Households SEMIA project. And that project it was in coordination with 4 European countries and 12 partners, and countries were Switzerland, Germany, Denmark, and Norway. And the objective of that project it was that by taking the aggregation of the loads within the distributed network of the specific loads and taking the aggregation of renewable energy sources prediction at a centralized point, that we call it as a backend system or backend server. So backend system is going to work as a virtual power plant. So in that project, we had the virtual power plant, which was located at Germany, okay, but it was considering or it was taking into account the loading condition and the renewable energy production conditions of Switzerland and Norway. And here you can see that how this cyber physical system, they have been coordinated with each other. And now we're talking about the centralized EV charging coordination. So in that project, the virtual power plant, which was located at Fraunhofer, Germany, and that Fraunhofer, Germany, okay, used to take the aggregation or the prediction of the specific load demand of the area where we want to control or shift the operation. And at the same time, for that particular area, how the renewable energy sources prediction is going to be there. Based on that, how the demand side management scenarios has to be generated, and considering the load, a specific load, so that specific load can be electric vehicle. So virtual power plant or the backend system is in a position to generate the demand side management scenario, or in a simple way to change the scenario of the electric vehicle charging of the individual customers in the within the distributed network, right? Considering the user preference also, then that backend system used to send the signal or the information using 3G communication to the front end system, that is the home energy management gateway. And then through the home energy management gateway, we were in a position to shift the operation of electric vehicles charging, right? So centralized electric vehicle charging coordination is going to work in this way, okay? And here, then another very important point which you have to keep in mind when we are doing the communication and when we are using the cyber physical system. And within the cyber physical system, when we are using the communication and collecting the data from all these points and together, right? So we have to be very careful about security and privacy. So because it is going to work as an IoT based system, so there is a chance that someone may be in a position to hack and shift the operation of electric vehicles. So then user may be in a position not to may not be in a position to charge the electric vehicles, or maybe overcharge, or may its battery get made damaged also. So here you can see that how the centralized electric vehicle charging coordination is going to work using centralized demand side management scenario, and that such type of coordination is going to work in a very systematic way if we have the smart distributed network within the smart city. Now we will come to the second option, that is a decentralized electric vehicle charging coordination. In decentralized architecture, each electric vehicle or group of electric vehicles connected to an aggregator as given in the figure above. So it works as an independent decision makers, okay, who decides its own optimum charging schedule in coordination with the central operator. So here we can see that it is going to be coordinated, right? Or it is going to get the signals from the centralized server or maybe from the backend system, but the user have the preference depending on the grid constraint, right? And depending on the situation, how he has to manage the local electric vehicle charging. So the local electric vehicle charging, maybe the individual electric vehicles, or maybe the group of electric vehicles charging also. So when we have the group of electric vehicles charging, so then that point can be the parking lot, or that can be a electric vehicle charging station also, or that can be maybe, let's say, the institutional or institutional parking system, or maybe the supermarket area and like that. So here, when we have one aggregator there or decision maker there, right, for decentralized EV charging coordination or the management, so this unit, again, it is going to get the information from the backend system or from the virtual power plant that at a particular time, how we have to shift the operation of electric vehicle charging. Okay, so that, but here the user have more flexibility, and in the centralized EV charging station, user doesn't have the flexibility. Only the it has been managed through the centralized point. But here, this aggregator or distributed aggregator has more flexibility to manage the operation of electric vehicle charging. So I believe that you might have been in a position to understand decentralized and centralized electric vehicle charging system. Now let's come to the centralized EV charging coordination. So how it is going to work? It has been explained through this picture here. So when we have the centralized electric vehicle charging station, and of course our coordination, and of course we know that all electric vehicle charging units, they will be located within the distributed network. So here, based on the grid coordination, so here the grid coordination means, like, at the centralized point, considering the load flow analysis within the distributed network. Here you have to keep in mind, we are talking about the load flow analysis not at the higher voltage level or the medium voltage level, but we are talking about the load flow analysis within the distributed network. So by doing the load flow analysis within the distributed network, considering the constraints of individual distribution or the feeder line, okay, then considering the low electric vehicle loads which have been connected in different feeders and so on and so forth. So based on all this information, right? So here we are going to utilize the information communication technology, engineering also, and of course the electrical engineering also, and the control system also, and of course the market economics also. So based on all this information, this centralized point is going to make the decisions, right, in the centralized way. So where user doesn't have the flexibility, and going to communicate let's say in next 1 hour, this feeder is going to have this much load. So you can have this much electrical vehicle charging availability in that particular feeder. So in that particular feeder, let's say we know that there is a one station. So that station knows that for next 1 hour, how much electric vehicle charging he or she can do like that. So here that even the electric vehicle charging owner or station operator doesn't have that flexibility. He has to depend on the information which is going to come from the centralized point, right? So here, with the help of this picture, right, you are in a position to understand how we can do the centralized EV charging coordination. From one point, it is good also because it has the control from the upper layer, but user doesn't have the flexibility. It is same thing, it is happening with our petrols also, or the diesels also, because we know that how much supply it is going to come, right? So based on the supply, then the we are going to fill. If we are not getting the supply from upper side, right, so then we may not be in a position to fill our petrol cars also. So but here with for the electric vehicle charging coordination, everything is depending on the electricity infrastructure, and that electricity infrastructure specifically of the distributed network. And then on the higher voltage side or the medium voltage side, we have to consider that within the 1 year time, 1 hour time, like how much energy we are going to be available, considering the prediction of the load, considering the prediction of the electric vehicles, considering the prediction of the intermittent renewable energy sources. Based on that, the operator can make operator at the backend system, that is a virtual power plant, which we can say also, like will make the decisions and will communicate those decisions of electric vehicle charging loads to these different aggregators. Okay, so now we will talk about decentralized electric vehicle charging coordination. Decentralized electric vehicle charging coordination is very good, and where the user, they may have more flexibility. And decentralized electrical vehicle charging station is going to help or contribute further going to contribute further for integration of distributed energy resources within the distributed network. It means that when we have the local energy controller, so our local coordination unit, so the local coordination unit can consider the integration of intermittent renewable energy sources, maybe energy storage also, or maybe conventional distributed generator also. So here in decentralized electric vehicle charging station, we have the first layer is distribution system operator level. And with reference to the grid coordination and utility constraints, so the local unit of energy controller. So basically that is, let's say it is going to be the charging station management, electric vehicle charging station management. So that unit has going to get the information from the backend system, like your load should be this much for next one. This energy controller has the options like how he or she can manage the charging of different electric vehicles, maybe some with fast charging, maybe some with slow charging, or maybe the combination. Then again, another point here, someone may go for the fast charging, some maybe go for the slow charging. So then there is going to be a different pricing mechanism also. So that different pricing mechanism has to be controlled or managed by this energy controller one. So who is going to pay more? And with reference to the available capacity, how much maximum charge can be available to that particular electric vehicles, let's say in the next 15 minutes or 20 minutes of time, right? And similarly for the slow charging also, because we know that if we consider the Tesla or very high capacity electric vehicles, those who are having the very fast charging, for example, Audi or maybe Volvo or maybe Volkswagen, right? So they are providing that in one charge, their car can go up to 500 kilometers or even more than that. Also, some of the car manufacturer they are claiming. So those cars are need fast charging. Of course, they can operate through the slow charging also, but when they want to have the fast charging, right? So that demand is going to be increased, and it will take around 15 to 20 minutes to get the fully charged that electric vehicle battery. And the capacity of that may be, let's say, 50 kilowatt or even more than that also. So then how this energy controller has to manage that operation, that is going to be a very key point. Okay. And then here you may notice that when we are using the decentralized electric vehicle charging coordination, we have the limitation from the grid or from the supply side. Okay. Then of course, then this charging station, they want to make the profit also, and they want to make the proper coordination. Then there is an opportunity to introduce distributed energy resources, so that during the off-peak time, if we have energy storage at that point, we can get it charged, or accordingly, we can do the management. And for that purpose, we need to have appropriate architecture. So that architecture we are going to discuss. Is it okay? Are you able to follow now?
Yes,
So
sir.
here,
Yes, sir.
yeah, very good. So in the slide number 6, you can see that I have given you an example of how the decentralized electric vehicle charging is going to be looking like that. So here you see that we have the decentralized electric vehicle charging, okay, and we have the charging points of different capacity. Some may be for the fast charging, some may be for the slow charging also. So now the charging management or the coordination of the electric vehicle charging has to be done, right? How much power limit or the grid constant is going to be there for next 1 hour? That has to be managed by the EV charging operator. So here, I mean, in normal petrol station, we know that our petrol pump operator, he knows that how much capacity of tank he has available, and then he just used to fill it, right? We used to fill it, right? But he knows that when it is going to be empty, when the next tanker is going to come and fill. But here, it is all these things are from the electricity. So that electricity supply, right? And we know that we have limitations of the electricity supply because at a particular time, we cannot overheat our cables or the transmission lines or the distributed network power lines also, right? So due to that, we need to have more proper coordination at the electric vehicle charging station. So here, what I want to say that if we are moving towards the sustainable transport, and we know that many car manufacturers, they are working very hard in developing different type of battery technology, different type of in vehicle inbuilt charging station, charging management units, and so on and so forth. So, but as a user or as from the charging point of view, right, we are not in a position to change that configuration. Okay, so from user point of view, we can manage when we want to charge, how we want to charge, like that. And then we have to work maybe very locally also, right? So here the point is that basically it is more like a reliability of the electricity, and how we can have this energy swaraj or energy independence locally, right? By using this local or decentralized EV charging management system. So here you can see that based on the grid constraints and the supply which we are going to get from the utility, this energy controller is going to manage the energy flow or power flow, whatever you call it, for the different electric vehicles by the slow charging or fast charging and so on and so forth. And everything nothing is free, right? For everything we have to pay. So here some of the vehicles which are going for the slow charging, they may have to pay less. Some of the electric vehicles, they may go for the fast charging, so they may have to pay. So all this pricing mechanism again has to be controlled by this energy controller. So here you can see that how the research opportunities are there, especially considering the local conditions into account. Right. So let's say if we consider your Valsad area distributed network, so you people have very good idea of that distributed network, right? You have all the parameters available. You know that how much power supply is going to be there. You know the locally that how much electric vehicles penetration is going to be there. So by considering your local conditions into account, local distributed network constants into account, you can develop the decentralized EV charging management system. Okay, so basically it is going to be an algorithm, right? That algorithm is going to be embedded in a system who is going to provide us the charging station, right? So that charging station basically may be going to provide by Schneider or maybe Fortune or maybe some in an international company, right? But that charging management system, it is going to have the flexibility to do the programming based on fast charging, slow charging, considering the local pricing mechanism, considering the local electric vehicles capacities, like how much capacity of electric vehicles are available and so on and so forth. So for that purpose, as a local, we need to provide the information to the supplier of the electric vehicle charging station, or maybe in coordination with them, we need to develop the algorithm and get it embedded into that system. So here you can see from the academic point of view, how we can do further contribution in developing decentralized electric vehicle charging station. Now, with continuation to that one, here you can see that what type of issues we are going to face. We are going to face many issues. For example, what type of charging mode is going to be there, how much charging time is going to be there, and if it is an electric vehicle charging station or parking lot, or maybe let's say institutional parking station also. So there may be, we may have some limitations of the electric vehicle units, charging units also. So of course there may be some waiting time also for, and we have to see that how day-to-day frequency is changing, time of the day, at what time most of the customers they are coming at, right? And then location. So all these factors, right, which we need to consider, in developing the controller for decentralized EV charging station. Then another thing, that we need to mitigate the peak demand also, and also we need to mitigate distributed network losses and congestion here. So here you can see that, so there are many energy controllers here. It means that many charging stations are there. So these charging stations, right, they can do the coordination among each others depending on their locations, right, considering the distributed network topology. And by considering all these factors into account, right, we need to make a proper algorithm. And make another point, let's say this one charging station and another charging station, the owner of these charging stations may not be the same, they may be different. If suppose they are the same, right, so then they can do some coordination. Let's say at one charging station there is a more peak demand or more demand, or more vehicles are there, on another charging station there is not that much demand. So then this charging station can direct some of the electric vehicles to go there and get it charged and provide some financial incentives also. That demand, and we want to mitigate the peak demand also. So all these factors we need to consider into account. Now we are coming back to the main point. We have seen that if we go to the previous slide here, in the previous slides, you can see that when we have the electric vehicles and like that, and we have all these factors into account, right? Due to that, there may be some limitations, and to overcome those limitations, right, we need to introduce local energy resources. So for that, we need to develop some new architecture. So here in this picture, or in this slide number 8, uh, in this slide number 8, solar photovoltaic based coordinated electric vehicle charging system have been described. So I will explain you how it is going to work. Then we will see its architecture also. So in the previous slides, we have seen that there is going to be limitations. There is going to be the limitations of the electric vehicle charging if we don't have the distributed energy resources, because that limit is going to be affected by the distributed network topology or the distributed network constants, including the transformer which we have kept at that level. Okay, so to overcome all these problems, let's say we want to introduce solar photovoltaic based charging station or solar photovoltaic based distributed energy resources. So when we are talking about the solar photovoltaic, we know that it is intermittent in the nature and it is going to produce the electrical energy when the sun is shining. Okay, and throughout the day, solar radiation is varying. So therefore, we will need appropriate energy storage also, because we know that electric vehicles, they may come at any time, and right, so it may come anytime during daytime or night time, and we have to charge them. So let's say we, if we have one electric vehicle charging station, and depending on the available space, again, this is another very important point. Depending on the available space at that charging station, we can calculate how much capacity of the photovoltaic panels it can be there. At the same time, considering the grid constraints, okay, considering the profile of electric vehicle charging with expected increasing penetration also, we have to design or find out the appropriate capacity of the local energy storage. Okay, so that is a very, very important point. So when we have the local photovoltaic with energy storage, that can work as a one distributed energy resources. And this distributed energy resource unit can help us to improve the power system stability as well as the power quality, and of course to operate that electric vehicle station at the unity power factor. Okay, so it means that reducing the reactive power demand also, so that is going to be possible also. So how we are going to do that? Now the next question is that how we are going to design the operational architecture of this. Is it okay? So here you can see that basically this electric vehicle charging station is going to be connected through DC to DC power conditioning unit. Okay, because we need to provide the DC supply to the charging points here. So here you can see that on this DC to DC converter, we may have one DC bus. And on the DC bus, then we are connecting the photovoltaic and the energy storage. And of course, then we are getting the power supply from the grid. And that is also going to be converted into the AC to DC here, right? And then that with that AC to DC, then DC to DC. So it is going to work back to back converter, and through designing appropriate power conditioning mechanism, we can operate it at the unity power factor and by making the reactive power to the zero. And in that, if we want to operate it as a back-to-back converter, then we can also put the grid constants also. So it means that whenever we have the active demand more here, and active demand due to the back-to-back converter has been limited, then here this local distributed energy resources is going to provide that deficit to here. So that is going to be provided by the energy storage, and if depending on the availability of the photovoltaic. So for that, we need to operate this as an active generator or as a virtual synchronous generator. So that we are going to study, and that we are going to discuss in this today's lecture also. Now here, I mentioned in the previous slide that uh, we want to utilize, let's say, get it focused now, that we, as a photovoltaic, as a main renewable energy sources. Okay, and that source we want to use, right, for supplying the electric vehicle load. And when we have the electric vehicle load, okay, so that electric vehicle load, it can come at any time, okay, and then we want to provide the power immediately, okay, but we may have the grid constants also. So depending on the grid constants and the availability of the local energy, right? So then this photovoltaic and battery has to operate as a dispatchable power source. So this is a very interesting point here. So this dispatchable power source, right? So for that, we need to include the functional characteristics, for example, group characteristics, okay, within the photovoltaic and battery operating mechanism, right, or in those power conditioning units, right, for supplying the load in a coordinated way, taking into account the grid constraints. So here you can see that for the local condition, or considering the local distributed network limitations and availability of the or penetration of the local electric vehicles and like that, we need to design the architecture considering the local conditions. For that, we need to have the local expertise or the person who is having the local technical knowledge of distributed network, local technical knowledge of the electric vehicle charging patterns also, and of course the local knowledge for the how much photovoltaic and battery capacity are going to be there, as well as the local knowledge of energy pricing also. So all these factors are going to be integrated in this control system. So here I will explain you the control system or how this DC coupled architecture is going to work for photovoltaic based active generator for electric vehicle charging station. So in order to overcome from the issues which we discussed previously, so if we have the uncontrolled PV integration, right, so that is not going to help us. We need to have the controlled PV integration. For that, we need to have the PV based active generator. So when it is going to be have the PV based active generator, when we are going to integrate the energy storage with PV, and this combination of photovoltaic and energy storage is going to operate as an active generator so that it can provide the power in a controlled way or as per the demand of the load. One of my PhD student, he completed his PhD. So his PhD focus was also on photovoltaic based active generator within the distributed network. So we are using that work, his work, in another PhD student's work for developing electric vehicle charging management architecture for the distributed network, and especially considering parking station, or maybe not from the individual point of view, or maybe from the, let's say, institutional charging station, or maybe supermarket and like that. So now coming back here to explaining that how photovoltaic based active generator is going to work. So here we have the photovoltaic, and here we have the DC to DC converter. So all we know that, so it is going to operate at the maximum point. But again, here we have the battery. Okay, so for this battery, right, again we have the separate unit DC to DC converter that is going to be bidirectional, and here we are going to have the DC bus. Okay, and we can have on the DC bus another electric vehicle charging load, but depending on the situation, what type of electric vehicle charging mechanism or infrastructure is going to be there, so we can put here on the AC bus also. Then we have the DC to AC and like that. So considering the grid limit here, so here we can see that the inputs of the real power, reactive power, because that reactive power sometimes we may have another load also here. So considering all these points together, all these points are going to be given as an input to this unit, and based this unit then is going to have group characteristic functions, right? Basically taking into account the local load supply and going to provide. So here you can see that we have the DC bus. So some of the section of this one is going to be working on DC microgrid architecture also. Okay, and if we consider there as in one unit here, then it is going to work as an AC microgrid architecture, right? So here we have the combination of DC and AC microgrid architecture, and the objective is that how we can utilize them, especially for the electric vehicle charging station, right? So now here in this picture, you will see that how the different units have been connected together on the AC bus to operate as an hybrid architecture, maybe I can say, and to supply the load, right, for the electric vehicles. Now here we have, you might have seen here, there are two energy storage. One is battery and another is supercapacitor, because we will need both. Supercapacitor is going to help us for the fast charging or maybe to overcome the sudden transients or the sudden peaks. And battery is going to provide us more like in a constant or the steady flow. And of course, we have the photovoltaic. So here you can see that photovoltaic and the energy storage, they are the DC device. So here we have the DC to DC converters, they are coupled. So now here you can see that for each unit in this architecture has different DC to AC units, right? And why it is different? That is again a very important point here. Why it is different here? So here we have for the photovoltaic, we have the DC to AC here. So here maybe we can operate this photovoltaic array unit as an direct injection of the power into the network. But with the battery and supercapacitor, with this DC to AC, or we can operate them at with some group characteristic function and bidirectional way, so they can contribute as an controllable or dispatchable power source. So this is going to help us in developing the photovoltaic based or maybe renewable energy based with energy storage, charging station infrastructure and its management, considering the electric vehicle load demand. So here you can see that power generation subsystems have been explained, energy storage subsystems have been explained. Then another very interesting is power conditioning devices subsystem, and on top of that, energy management system. So that is, and then again, it is going to have the hierarchical approach also, or hierarchical control, right? So this is going to be a very complicated also. And because here we have the very different type of load, electric vehicle charging load, which we are talking, and you want to use the, of course, the grid is going to be there, but we want to have more utilization of the local photovoltaic and the energy storage. Now here with the PV array, right, it is going to be operating at the maximum power point and going to inject the power to the AC grid. And at the same time, then considering the grid constants here, the limits, right, then we have to see that how the battery and energy storage are going to contribute with reference to those both 2 points, right, for fulfilling the local load. So this is a very interesting point. Then it comes, the main thing is the developing the architecture. So for that architecture here, you can see that all these power conditioning devices has to be controlled in a hierarchical way. So how we have to design the control mechanism for that. So that I'm going to explain you in much more detail. So here with hierarchical control, depending on the availability of the energy from the battery and supercapacitor, as well as considering their discharging pattern or the discharging time constant, the group functionality is going to be implemented into this power conditioning devices, and that has going to be controlled through this hierarchical control. So here in next in this picture, you will notice that how this hierarchical control is going to be work. So here we are going to have now three sources. One is photovoltaic system, another is battery system, and another is supercapacitor system. So every unit, they have their own switching control unit. Then of course, then our next one is going to be the power flow control PFC unit for all these things. And then we have to do that control of power dispatching. Okay. And on top of that, we have to see that control of working mode also. So let's say depending on the electric vehicle charging load pattern or a load, then he sometimes the capacitor may be in a position to help to overcome the transients. From the energy point of view, the battery system, and of course the photovoltaic is more like providing the energy, but it is going to the grid. So maybe from that point of view we can consider. So here this is here you can see that how the different hierarchical level is going to be there: switching control, power flow control, then control of power dispatching, and then control of working mode. So these control of working mode have been explained in this slide now. So how the power flow and switching control is going to work. The main function of this hierarchical stage is to calculate the reference values for PWM switching controls of VSIs, okay, which is connected with the PV array, and the centralized energy storage based on the control parameters received from the CPD level. So here you have energy storage. Here you can see that. And then here we have this control unit. So here in the control unit, PV array is going to inject only the active power to the AC bus. We are going to operate that as an as unity power factor. Okay, but the centralized energy storage is going to compensate the intermittency of the photovoltaic with grid constants. Right here, you have to keep in mind with grid constants. Right, grid constants means like we are going, or this unit is going to get like some load limitation values from the centralized operator. For example, for let's say in our 11th hour, this unit should not have that, should not take from the grid this much value, and let's say at hour number one should not cross that. So all those factors then we can include here in this one. So that's why it has been mentioned here. The centralized energy storage is going to compensate or going to help to respect the grid constants there. Okay. Then active and reactive power demand of the AC load in coordination with the grid. Okay, that is okay. Therefore, the power flow control with frequency stability has to be considered. Okay, and then in some condition, if suppose we don't have the only the AC load, sorry, real power load, if we have the active P and Q load, then of course, then we have to use the reactive power group characteristic functionality also. And how then we have to use this group characteristics, especially in the battery and supercapacitor units, where we can use the frequency control loop. So here, this frequency control loop, right, has been explained for the switching control of energy storage, and those are going to be a very different for battery and going to be different for supercapacitor also. Okay, so that have been explained here, and of course I'm going to share some results with you also. So then moving forward, so here you can see that The overall control system has been developed as a hierarchical system with state flow control and group characteristics. The hierarchical control is very much suitable for this type of real-time power management, as it helps not only in managing and controlling the power flow, but also helps in maintaining the safety and stability within the system. So what does it mean, this point? So this point, it means that we need to have the hierarchical state flow control for the electric vehicle charging station, where we are going to integrate photovoltaic with energy storage. This photovoltaic and energy storage combination has to operate as a dispatchable power source. In this work, I mentioned that photovoltaic can be connected to the network independently. Okay, just like only injecting the real power into the network, but combination of supercapacitor and a battery bank can be operated with group functionality, right? Can be operated with group functionality for providing the electrical power for the local electric vehicle charging, considering the grid constraints at that particular time. And the architecture which have been shown, have been described here, basically that is based on AC microgrid architecture. So now here we have the three conditions. One is supercapacitor, its charging availability, and it has a different discharging characteristics. Battery bank, it is have again different characteristics. How much charging availability, what type of operational characteristics are there. Then another thing, like combination with the PV and the grid, because we are taking the PV as injecting the power directly into the grid, and of course the grid constants. So considering all these three factors into account, right, we need, and then of course the load is also there, and the load is electric vehicle charging load. So considering all these parameters into account, we need to have some hierarchical system with state flow control, and accordingly implementing the group characteristics in the VSIs of or voltage source inverters of supercapacitor and the battery bank. So in such type of topology, the topmost level should select the appropriate working mode based on the rated power values and the grid constants, considering the whole system as a one unit. The subsequent layers concerns the individual units of the active generator system. It is going to help to keep the state of charge of the centralized energy storage units at relatively high values, because the system switches the energy storage elements between charging and discharging mode. Power dispatching layer is going to play the major role in keeping the state of charge of the energy storage unit at a high value, which in consequence leads to maintain the active generator system availability for the continuous operation. The centralized energy storage elements, that is lead acid battery and supercapacitor, are going to decide the power share at a layer based on the active state to compensate the power fluctuation caused by the PV generation, load, and taking into account the grid limit. Grid is connected to the active generator system with demand limit, so sudden power system stresses could be avoided and the grid stability can be accomplished. Okay, so this is a very interesting point. So based on this, right here, you can see that all these parameters, how we need to integrate in developing the energy controller or energy electric vehicle charging management system. So from the research point of view or from the academic point of view, I have given you a very good hint, right? So consider the local conditions into account. And let's say we want to have the energy storage. We want to utilize the local solar photovoltaic system also, maybe local distributed generator also. And of course, then we have to consider the pricing also. So then here we can consider this energy controller or charging unit like that. So accordingly, we can manage the charging of different electric vehicles.
And this is called the transfer rate boundary. Transfer rate boundary direction.
Is it okay?
Yes.
Yes, sir.
Very good. So now here you can see that, I mean, basically from learning point of view, because I know that many of you may be interested in doing the PhDs also, or maybe doing some industrial project work also, or maybe doing some task for, let's say, for the Gujarat government or maybe for the central government also. Like, let's say how we can contribute in sustainable transport. So when we want to have more sustainable transport, the first question is that how we can have the electric vehicle charging stations, right? So that if we don't have that infrastructure properly available, so even people are buying the electric vehicles, where they are going to charge, how they are going to charge, right? So we cannot control the buying of the electric vehicles, but I mean, as an electrical engineer or the planner, or like it is our duty, like to have to design appropriate electric vehicle charging station, right? Because government wants that to have too many electric vehicles, right? So that is good, but at the same time we have to see how we can develop such type of electric vehicle charging station unit. So here I tried to explain you, right, with the combination of the photovoltaic and energy storage, right, how we have to develop the energy controller and then accordingly manage the load, like some of the fast charging and some of them maybe of the slow charging here. So these are the references, okay, which you can refer for today's lecture. And then another thing, like a few years before, I published one book from the and it is published by the Elsevier. It is on electric vehicles prospects and challenges. So this book has covered many issues from the policy point of view, as well as from the electric vehicle batteries point of view, and how we can have the photovoltaic based charging station for the electric vehicles from different countries. Scenarios have been discussed, including Indian scenarios also. So if you are further interested, so I will request you to refer this electric vehicle book also. So maybe now I can stop here, and now we can try to have more discussion from the participants also. So we can so the participant can also get a benefit from my expertise or from my knowledge, and at the same time I can also learn from the participants also what type of challenges they are facing there and what are the ideas behind them, right? So I want to have more lively interaction. So maybe now we can have some discussion with the participants. And yeah, please. Yeah, because all the time I'm speaking here, so I don't know how's the reaction of the participants. That I want to see basically. And I want to have a discussion. Maybe we can start with a one by one also. Like, so how many participants are here? Oh, there is many, hundreds of them, right?
Yes.
So maybe a few questions, and what I feel, Harshal, maybe then otherwise we can take 5 or 10 minutes break, and then I can start then a second part of the lecture. So what do you advise? Yeah, then we will take second part and then we will do further discussion. Yeah. So please feel free to ask, right? Because I can see that the hundreds of people are there, and many of
So I will like to request you that if you have any questions, you can ask if you have any questions. Maybe anything related to this, so that after 5 minutes, sir can start the next session, next part of this session. Sorry.
Yes, let me ask one more. Sir,
yeah, yes, you can start your video also, right? If possible.
if we are looking towards electrical vehicles around the world, and let us suppose during or on or before office hours, if there is a high penetration of the electric vehicles in the grid, I would be happy to know which factors would be likely to be more cause of concern for us while doing some research. That is the
The
one.
basic, yeah.
And the second one is I would be happy to know about something FPGA controller also, if it is possible.
Yeah. So first point is that a very good point. First, we know that all our distributed network, they have their own limitations, right? All feeders and everything, and we know that how much load it is there and like that. So all of a sudden, if we have more electric vehicles and all the loads are coming for a charging at a particular time, right? Let's say to a particular electric vehicle charging stations, so depending on its limit, right? So it cannot provide the charge to all, it cannot provide the electricity to all the electric vehicles. Okay. So it has to do proper coordinations. That's why we discussed in this lecture that proper coordination is important. So when all the loads are coming, right, and everyone want to fill their electric vehicles, right, maybe the fast charging or the slow charging, right, so that electric vehicle charging station operator can help them or can provide the energy only if yes she have the distributed generator. It may be the energy storage or maybe some another source, right? So then because he has the limit from the grid, right, he cannot extend a particular limit. So for from that point of view, we have to design this charging station in such a way, like how much energy storage should be there or how much distributed generator capacity should be there, okay, and how much at a time, how many electric vehicles can be charged with fast charging, maybe with slow charging combination. So all those worst case scenario and best case scenario, we need to do the analysis. So the main limitation is going to come from the distributed network limitation or the constants related to the distributed network. And second point regarding the controller. So we can use any controller. FPGA controller is very good. So, but within that controller, whatever, like embedded system which we are going to use, the main thing is that how we are designing the algorithm considering the local condition into account. If your algorithm is ready by taking into account all the local conditions, and if we are tested it in a, let's say in the simulation mode or whatever, then any charging management or electric vehicle charging station manufacturer, he or she can be in a position to embed that algorithm in their unit, right? So I mentioned you earlier that if we have the centralized charging unit, so centralized charging unit, basically, it is going to get the information from the upper end and going to provide the information to the load how they have to shift, but the load doesn't have the flexibility to change. So such type of system, like we used the in a very simple platform, like Ogema platform was there, and in that we put some Java code there, and it worked very well, right? So whatever the controller you can say, right, depending on the supplier. The first thing is that how we are going to develop the algorithm, right, for that particular charging station, considering the local constraints into account. Is it okay?
Yeah, thank you, sir. Thank you.
Any other question?
Participants, if you have other questions, you can ask.
Yes, please read it. Please read it. Yes, this is a very good point. And for, let's say, you, I don't know the candidate or participant is from which area. Let's say if we consider any,
Sir,
for example.
good morning, sir. I am Anand Raj. I am from Karnataka, sir.
Very good. So let's say you want to design one electric vehicle or couple of electric vehicle charging station for, let's say, for a some reason in Bangalore, for example. So for that particular reason, right, or that particular distributed network, right, you know the distributed network topology, right, the parameters of all power lines, existing load profiles, and like that. So within the distributed network, right, we know that, so how much the grid limit is going to be there, okay, and we want to have one charging station there. So to design that charging station or to find out that charging station, we need to do the power flow analysis within the distributed network, considering this electric vehicle charging station also and the grid limit also. And then in that point, we may need to expected electric vehicle charging pattern profiles also with increasing penetration of electric vehicles. So based on that, then we can see that, yes, how we have to do the load distribution, how much capacity of the electric vehicle charging station can be there. So depending on that capacity at a particular time, how much electric vehicles which you can charge, because we know that now the in market the electric vehicle capacities are increasing exponentially now, right? So all those factors we need to take into account, and then based on that, then of course we are going to take the charging units commercially available from different international manufacturer or suppliers basically. And then, but when we are going to get those units there, but then the question is that we have to provide the charging to the local electric vehicles, but at the same time we have to consider the local pricing mechanism also. And then again, someone who want to go for the fast charging, someone who may want to go for the slow charging, then we have to do those combination together, and accordingly then we need to design this charging management system. And it is going to be everything is going to be IoT based. So all these things, because every charging unit, they may have its own mobile communication unit and like that. So all those factors then we need to consider, and for designing the operation management of electric vehicle charging station. So it is going to be multidiscipline approach. It is not only just designing the DC-DC converter or DC to AC converter and like that. Okay, so because DC to DC converter, AC to DC converter, they have been widely used. Okay? Now the main question is that how we have to control them, and the control of them is basically depending on fast charging, slow charging, considering the pricing mechanism, operating them as an active generator also, like that. Is it okay?
Yes, sir. Thank you, sir.
Any other questions?
Participants, if you have other questions, you can ask.
Very good. So shall we take 5 minutes break? I will just take a cup of coffee and then again I will start. Is it okay?
Yes, sir, sure.
Because I'm speaking continuously from last more than 1 year, 1 hour, I think, right? Yeah, it's going to be 1 hour 30 minutes, right? So maybe just I will take a little break, bring a cup of coffee, and then after that, then we will do some general discussion about the electric vehicle system. Okay.
Okay.
So now it's okay. Very good. So I'm just trying to get that my screen here. It is not coming. Give me 1 minute. I have second presentation, which is on charging management. That I'm not able to get here because it is on my OneDrive. One minute. Are you able to see my screen? Only video. And because that second file, what I'm trying to look is I'm not able to get it here. It is on my OneDrive. So I will use, because now we don't have that much time left also. Yeah, 25 minutes. So I will explain. Yeah, this one I will explain because it needs a lot of technical input here. Okay. So this is a very interesting slide, which is going to be used for the charging management of the electric vehicles. So here you can see that we have two layers. Okay. And in this, especially, let's say, let's come to the frequency control loop and voltage control loop. So here in the frequency control loop, which is going to be used. Now my slide is visible.
Yes, sir.
Okay. In the frequency control loop, when the load is going to be increased and this most of the electric vehicle charging station is going to be operating on the AC microgrid architecture. Due to that, the operating frequency at the common point of connection is going to be used for controlling or managing the dispatchable power from the battery and the supercapacitor. So that have been explained in this frequency control loop. When we have more electric vehicle charging, so of course the frequency is going to be changed. Okay, so with reference to the change in the frequency, here the PID controller is going to be used and going to be considered with reference power, because then another very interesting and very important point is here. We have supercapacitor, we have the battery bank, we have the grid limit also. So everyone is going to have particular load limit at a particular time, a particular supply limit at a particular time, and at that particular time we may have the different electric vehicle demand. Due to that, the local frequency may get changed. So that local frequency change going to be used as the going to be used with reference to the reference point and the reference power, okay, for sharing the load from different sources to fulfill this aggregated load of electric vehicles. So here within the load also, we may have fast charging load, slow charging load, and like that. Some may be paying more money, some may be paying less money. And from the supply point of view, we may have, let's say, one side uh, battery bank, they may have their own limitation, grid may have own limitation. So every source, they are going to have different group functionality. So those different group functionality, how we have to integrate right together here for supplying the load on this. And our target is that mostly to fulfill the load utilizing the local energy storage. So here you can see that we have the supercapacitor layer, PFC layer, and that layer, they are going to be providing the input to this DC AC power conditioning device, so that they can provide the power in a dispatchable or controllable mode for supplying the local load. So that have been explained here. So here you can see that in this all controllers, Clark's transformation have been used, where we use the DQ to ABC conversion and like that, and accordingly the PWM signals have been generated, and then these PWM signals have been used for the three-phase power control and like that. And then here we have the load here like so. And then similarly, not only from the frequency control point of view, then another point is from the voltage control point of view. Why it is going to be required? Because from the voltage control point of view, we want to maintain the constant voltage for supplying, because it is going to work and on the AC microgrid architecture. And at the same time, at the grid connection point also, we want to maintain the voltage within the limit. So to maintain the voltage within the limit at the grid connection point view, and if we are not using any static devices for that reactive power compensation, so for that purpose, this active generator, means like battery bank and the supercapacitors, they can help us to provide the reactive power. That's why here in the second unit, we have the voltage control loop also. And this voltage control loop inputs, you can see that it has been connected here and it has been used here in this energy storage controller unit. And this energy controller units, then here you can see that how these two different sections, right? One is with the PV and another is with the energy storage. They have been incorporated together here. So here, basically what I want to say, when we have number of electric vehicles with fast charging and slow charging, and when we have different distributed generators with different operational characteristics with grid constants, So in this case, they are the stationary sources like supercapacitor, battery bank, and the photovoltaic. So we implemented the group of functionality within the power conditioning units. And then accordingly, they are managing the power flow to the load depending on the fast and slow charging. Then another very interesting thing here, let's say if we don't want to utilize the energy storage, for example, for lead acid battery or the supercapacitor. But in place of that, if we want to use the conventional gas generators, okay, so those conventional gas generators already they have that inbuilt functionality, or we can or those governor mechanisms which we can include in the gas turbines, and they can also help us to supply the power to the electric vehicles based on the demand variations and so on and so forth. So are you get the point that you can do the power flow and switching control for managing the local vehicle charging load? Does the participant is in a position to understand the point? Yeah. So, I mean, maybe the participants can discuss here, because we have left with, let's say, 20 minutes. So maybe we can have further discussion here, because I had some problem with my second part of the lecture to get it here, because it was stored on the OneDrive. So I'm not sure that why it is not coming here. So no problem. So let's say with this last 15 minutes, we will do more interaction to know each other and to get the idea or your concepts, right, in doing this power management flow for photovoltaic based electric vehicle charging station. So maybe Harshal, you can start with you also, so that others they will get that. Let's say how we have to talk, and they will get some further queries based on your thread, maybe. Or
Yes, sir.
yeah, please.
Yeah, what happened? Yeah.
So now this slide is there, okay, and we will take this slide as the reference, and maybe we will start one by one, maybe for few people. Like, let's say maybe Vinod is there. I can see his name is on my top. So Vinod, what do you think, and what is your learning from this course or from this lecture?
Yes, sir. I already asked you two questions. One
Very
about
good.
the high
So yeah,
penetration.
that's very good. Then maybe we will move to the Sunil. Hello, Sunil. Are you there?
Vinod, sir.
Yes.
No.
Yes.
Yeah, I think Vinod already asked some questions, right?
Yes, sir. Yes, sir.
I want to see that people are there, or are they just kept their mode on like that. Maybe now we can go to the Vijay Patel. Is he there? Oh, so it seems for me like they might have kept their logged in, and they may be running out here and there.
Vijay Patel, sir, are you there?
No, it doesn't. What about Puneet, Mr. Puneet? Are you there? Maybe I think you should make the people like to have their virtual attendance. So we don't know whether they are present or not, right? And Mr. Pushpendra, are you there?
Many times there are mic issues. Sometimes like some people try to speak, but due to this microphone issue.
Okay, okay.
Yeah.
Yeah, maybe they can type otherwise. Yeah.
So we have a question here from Mr. Merua Bhaskar Reddy. So how can we bill for electric vehicle?
How we can?
Can we bill for electric vehicles?
Bill, electric bike. I mean,
Billing,
charging,
yeah,
right?
like charging, yes, charging for the electric vehicle.
Yes, that is a very important point. And here in Norway, you may be knowing that we have the 40% electric vehicles. And when we want to charge the electric vehicles at the gas station or like that, so there are two options: fast charging and the slow charging. So fast charging people, they have to pay more, and the slow charging people, they have to pay less. And when we go, then we have to tap our NFC card, or it's generally everybody have that NFC cards. So in that card, then our all credit card details are there, and then it will ask that what options you want. So 15-minute charge with this much capacity fast charging. So then there is having the different rate. If you want to go for the slow charging for how many times, so then it will be the different rate, and then automatically your metering will start. And then there's a charging rates also. Again, it is going to be varying with reference to the time also. During the peak time, more higher charging rate, and during the off peak time, the charging rates are different. So it is quite a dynamic also, and like that. Yeah. So basically, it is all online and the virtual mode payment, I can say. No human intervention is there.
So we also have one more question regarding the previous slide, I suppose. I mean, regarding the previous part, I suppose. How do we
Yeah.
get the access to the data required for the coordinated planning study?
Yes. So here the data basically we don't have that much data available from the electric vehicle side, but we have the data available from the distributed network and for the existing load side. Okay. So those data we can use, and then the data. Then let's say we have to select some electric vehicle load profile, slow charging, and the fast charging. Those are widely available in on the internet also, or maybe electric vehicle manufacturers they can also provide us, or they are available on their websites also. So we can say, let's say one electric vehicle there, we have 10 charging units there, so we can consider the worst case scenario and best case scenario, and based on that, then that charging station we can take it as a one load within that distributed network, and then accordingly we can do the analysis. Then we can see that if we take the worst case scenario or the best case scenario, how the voltage profile and the loading condition within the distributed network is going to be changed. So if those profiles are going to be changed and violating the limits, then of course we need to consider the distributed generator. Then we will put the distributed generator at that point, and then accordingly we will try to find out the optimum capacity of the distributed generator with that worst case scenario and best case scenario of electric vehicles, so that all the operational parameters within the distributed networks remain within the limit. So then accordingly, then we can make the design, right? So let's say, so those data we need to use. So at the first point, we need to have the operational data of the distributed network and the existing loads, and then at what point within the distributed network we want to have the electric vehicle charging station. And for the electric vehicle load point of view, then we need to take the load data or the charging pattern data of the electric vehicles from the Nissan Leaf, or maybe from Tesla, or maybe from Audi, or maybe from any other car manufacturer, and considering the worst case scenario and the best case scenario. Is it okay?
Yes, sir. Yes, sir.
Yeah, very good. Huh? Uh-huh. Yes, please, please. Yeah, because it is multi discipline or multi. Yeah. It's really, really difficult to say. Very, really, really difficult to say. Okay, because now this like how much battery capacity is there in that electric vehicle, right? It depends. Okay. Now earlier they let's say if we take the Nissan Leaf, it earlier they have the 24 kilowatt hour battery. Now new Nissan Leaf is coming around 62 kilowatt hour, right? So it is changing. It is changing. Okay. And then we have to see that, let's say whatever the electric vehicle battery we are taking, and then our electric vehicle we are selecting, let's say if we take 62 kilowatt hour Nissan Leaf, that new model, it says that in one full charge it can go to up to 400 kilometer. Okay, so we have to see our driving cycle, that 400 kilometer means how we are going to utilize that 400 kilometer, and to get that much units of energy, then we have to see that how much solar photovoltaic or whatever unit renewables we want to fix it, and whether we want to have more from the daily energy zero energy consumption point of view, or weekly or monthly or yearly energy consumption point of view. So then accordingly we have to make the combination of that one. So it's very difficult to say. And then another thing which you might have seen, that because I don't have that data in my mind, but some car manufacturer, they are trying to have vehicle integrated photovoltaic system. If the whole vehicle is having the full photovoltaic cells integrated, so then they are saying that in one charge of or one day, how much solar radiation is going to be there and going to be charged. So it is going to contribute around 60 to 80 kilometer driving per day. But those figures, not exact figures, are not in my mind, but it is in this range. Is it okay? In my opinion, vehicle to grid is not going to be a viable solution, because vehicle we want to get always fully charged, and when it is going to be available, and when it is going to be discharged, right, it needs a lot of analysis and a lot of conditions into account. Nissan Leaf, they have started some demonstration in Denmark, where they are using that, let's say the electric vehicle, charged electric vehicle can be used for demand side management of a particular house. Okay, not for the like primary frequency or on the bigger scale. So, and within that they have put some limits that depending on the user or customer, like how much reserve he or she want to keep into the electric vehicle charging. Always we want to have our tank full. Okay, so let's say if we want, if our electric vehicle charged is 100% and we want to put it 60%, let's, so then we have the 40% which we can play around, right? But at what time the vehicle is going to be there and like that, it depends. So most of the daytime it will be the out of the house, and in the night time it will be there. But in the night time we don't have any loads there, very low load, right? And maybe the nighttime the electricity pricing may be low. So it is very complicated situation. And many electric vehicle manufacturers, they don't want to play around their charging management system. If we play around, so then the vehicle warranty we are going to lose. So nobody want to lose the vehicle warranty, right? So therefore, and most of the car manufacturer, they are not in mood to do the bidirectional management system in their electric vehicle charging controller. So personally, I believe that. So it is not going to be a very effective, are not going to have the effective participation of vehicle to grid into the distributed network. Is it okay?
Thank you, sir. Protection means like from the health and safety point of view or from charging point of view. There are a lot of protections basically from health and safety point of view also, because we know that mostly lithium ion batteries are used. So they are very, I mean, their structure have been well tested, right? For example, if we have some crash, right, how much pressure it can sustain so that it cannot explode and like that. So from the health and safety point of view, let's say how much mechanical stress it can or impact it can sustain. That is a one point, right? And then of course, if something is going to happen, so how the open circuit means, like there should be disconnection of the load from the battery, right? If there should not be any short circuit, so all these protections have been taken into account. And then of course from the motor point of view also, but main protection is from the, if we consider from the battery point of view, so main protection is going to be have on the battery. And of course other protections are there, like those are the normal electric vehicle protection mechanism, or even in another vehicles also. Yeah. Overcharging mechanism also means like to avoid the overcharging, undercharging, keeping the minimum reserve, right? Doing all the time battery state of health estimation, battery state of charge estimation. So all those points are included, and those are displayed on the user platform, let's say, or on the user display. And those data are also recorded when we are going to have servicing of our electric vehicle cars. So then they will know that what is the state of health condition of your battery, right? State of charge estimation, and so on and so forth. Yeah. Any other question? No. Because you see, it is the same like in our mobile also. We can do the fast charging and the slow charging also, right? Earlier, the mobile used to take a lot of time to get charged. Now we have all mobiles, they get very fast charging and like that. So depending on the electrochemistry of the cells, depending on the electrochemistry of the cells, we will be in a position to do the charging, fast charging and the slow charging. And also, of course, the capacity of the batteries also. For example, if we take the earlier version of the Nissan Leaf, there we cannot have the fast charging. It was taking long time to charge. But now with the high capacity of the high capacity of the battery, we can charge in a very short period of time. Good. So I think we have a very good discussion and the presentation also. And I hope all of you have enjoyed it. And I hope that all of you may be listening to me also. Right. So I will stop here. Okay. And if you have any questions or any queries and you want to make further consultation with me or doing some cooperation, collaborative work, just feel free to drop me one email. Okay. Yeah. Thank you very much. Thank you very much, Harshal, and thank you very much. Kashyap is there?
No, sir. This was the last session for today.
Okay.
So I think, yeah, this is the last session.
Please convey my regards to Kashyap Mukari also.
Yes, sir. Yes, sir. He's also he's busy with some other meeting right now. So I'll definitely convey your regards. And
Yeah.
sir, on behalf of Electrical Engineering Department, the Government Engineering College, Valsad, I like to thank you for your time and for this wonderful session today on electric vehicles.
Because I have some technical problem on my computer. I'm not able to get the second file from OneDrive, so no problem. Okay.
Yeah, no issues, sir.
Yeah. Okay. Thank you. But I hope it was useful. Yeah. Okay.
Yes, sir. So
Thank you.
yeah, thank you, sir. Yeah. Are you able to? Yeah, am I audible, sir? Yeah. Okay.
Yes. Yes. Yes.
Fine, sir. Yeah, you may leave, sir. Yeah. Thank you very much, sir. So participants, with this, our day 4 ends here. I'll again request every one of you to fill the feedback. The feedback link will be shared shortly by our colleague here in the. Yeah, it is already shared in the group. So I request every one of you to fill the feedback. It is there in the WhatsApp group as well as in the chat box here, right? So please fill up the feedback for all the 3 sessions, and we will meet tomorrow for our next session. The next session will start at morning 10 a.m. It is the session expert is Dr. Bhim Singh from IIT Delhi. So let us stop our session here. Good day to all. Please fill up the feedback, everyone. Those who have filled up the feedback can leave the session. I am keeping this session on for just the feedback link.